If the deep sea released its creatures into our world, they would fall apart, literally. Let me show you why. Close your eyes and imagine being compressed under the weight of 100 atmospheres. Imagine living in eternal darkness where no ray of sunlight has penetrated for hundreds of millions of years. Imagine living with a cold so absolute that your metabolism slows to a crawl and where a single meal might be your last for months. Now imagine surviving there, thriving there. It's almost impossible not to become something unrecognizable. That is what the deep ocean does to life. The deep ocean doesn't simply host strange creatures, it manufactures them. Which means that every grotesque feature you see, every impossible adaptation, and every nightmare shape is an answer to a simple question. How do you exist where existence should be impossible? This video will tell you the story of how pressure, cold, darkness, and starvation conspire to create monsters, and how those monsters might not survive what comes next. Pressure is the deep ocean's first architect, as every 10 meters of descent adds another atmosphere of weight on any living thing. At 1,000 meters, the pressure is 100 times greater than at the surface. At 4,000 meters, it exceeds 400 atmospheres, and at the bottom of the Mariana Trench, 11,000 meters down, the pressure reaches 1,100 atmospheres, the equivalent of 50 jumbo jets balanced on your chest. So definitely this should be incompatible with life. And for most organisms it is. Human lungs would collapse at just 100 meters deep. Swim bladders? The gas-filled organs most fish use to control buoyancy would implode under this pressure. Basically, any creature with air inside its body would be doomed. But the deep ocean eliminates air as a concept entirely. That is why deep-sea creatures have no swim bladders. Their bodies are composed almost entirely of water and soft tissue, so they don't collapse under pressure. They become soft, they become gelatinous, but all of that comes at a terrible cost. These creatures cannot survive at the surface, so they remain prisoners of the deep, held together only by the crushing force of the abyss. In 2003, marine ecologist Karen Parkinson was trawling the seafloor off New Zealand when her nets hauled up something that would become infamous. A pale, drooping mass with bulbous features and a downturned mouth that seemed to embody existential despair itself. She photographed it and nicknamed it Mr. Blobby. The image went viral, and in 2013, the Ugly Animal Preservation Society crowned it the world's ugliest animal. Memes spread across the internet. The blobfish became a symbol of nature's capacity for grotesque mistakes. But here's the truth. We were only looking at a corpse. At its natural depth, which is between 600 and 1,200 meters, the blobfish looks like an ordinary fish. It has bulbous eyes, feathery pectoral fins, and a pinkish-gray body that tapers to the tail. It hovers right above the seafloor, with its gelatinous flesh held rigid by external pressure. But when brought to the surface, that same flesh loses all structure because the pressure that once held it together is gone. So its skin sags, its features droop, and it becomes the blob. In a nutshell, the blobfish isn't ugly, it's dead. And we mistook its death for its nature. That right there is the paradox of deep-sea life. Creatures built for pressure cannot survive without it. Their bodies are architecture designed for a world we cannot enter. Remove them from that world and they collapse, disintegrate, transform into something unrecognizable. The deep ocean makes monsters that can only exist in the deep. Here is the second paradox you need to know. In a world of starvation, giants thrive. The deep ocean is essentially a desert. Food is scarce, arriving only as a slow rain of organic debris drifting down from the surface, which means a whale carcass might fall once in a generation. In this environment, you would expect life to shrink, to conserve energy, to become small and efficient. And yet some of the largest creatures on Earth live here. The colossal squid, for example, reaches 14 meters in length and weighs up to 700 kilograms, the heaviest invertebrate ever to exist. Giant isopods grow to 45 centimeters, the size of a football. Japanese spider crabs span 3.8 meters from claw to claw. The explanation for life growing enormously in the coldest, darkest, most food-scarce environment on the planet lies in two factors: oxygen and metabolism. Let me explain. Cold water holds more dissolved oxygen than warm water. At minus 1.8 degrees Celsius in Antarctic waters, oxygen saturation is nearly twice that of tropical seas. More oxygen means bodies can sustain larger sizes without suffocating. But there's a second advantage also. Cold slows everything down, meaning metabolism crawls. Growth takes decades, and maturity comes after a century. The Greenland shark, for example, doesn't reach sexual maturity until 150 years old and can live for 500 years. So, in the deep, time moves differently. This then creates an equation. Large bodies are metabolically efficient. According to Kleiber's law, a creature 100 times heavier than another consumes only 32 times the energy. So when food arrives once a year, efficiency is survival. The giants can fast for years. The giant isopod can go 5 years without eating. When a meal appears, they'll initially gorge grotesquely, distending their bodies until they can barely move. Then they wait in the darkness, but it gets even stranger. The colossal squid, which is the heaviest invertebrate in the deep sea, doesn't just benefit from one type of gigantism, it exploits two. It lives in polar waters around Antarctica, where polar gigantism occurs, and it hunts between 1,000 and 4,000 meters, where abyssal gigantism dominates. So the colossal squid is the convergence of both phenomena, pushed to an extreme found nowhere else on Earth. However, the colossal squid's most monstrous feature isn't its size, it's its eyes. At 27 centimeters in diameter, the size of a dinner plate, they are the largest eyes in the animal kingdom. Larger than a whale's, larger than an elephant's, larger than any eye that has ever existed, and they serve a singular purpose: to see in near total darkness. At depths where sunlight cannot reach, the colossal squid hunts the one creature that can threaten it: the sperm whale. These whales dive to 2,000 meters to hunt squid, and when they do, their massive bodies create faint bioluminescent trails, disturbances in the water that trigger glowing plankton. The colossal squid's enormous eyes evolved to detect this glow from 120 meters away, searchlights in the void scanning for the faint glow of approaching death. Those eyes do come with a cost, though. They require enormous energy to maintain, they occupy space that could be used for muscle or gonads, and they make the squid vulnerable, so sensitive to light that bright submersibles likely blind them temporarily. This is why we've never filmed an adult colossal squid alive in the wild until 2025. That's right, in March 2025, exactly 100 years after the colossal squid was formally identified and named, scientists finally saw one alive in its natural habitat. The footage was captured by the remotely operated vehicle Sebastian, deployed from the Schmidt Ocean Institute's research vessel Falkor 2 near the South Sandwich Islands in the South Atlantic Ocean. At 600 meters depth, the ROV's cameras caught a translucent form drifting through the water, a juvenile colossal squid, barely 30 centimeters long. For 100 years, we had known the colossal squid only through remains found in whale stomachs, scars on sperm whale skin, and a handful of dead specimens dragged up by fishing nets. We had never seen one alive, never watched how it moved, never observed its behavior in the wild. The juvenile was almost completely transparent, typical for glass squids. You could see its organs, its pearly eyes, the hooks along its tentacles. As it matures, it will lose that transparency, its body thickening with muscle until it becomes the dark red behemoth that battles sperm whales in the abyss. But in that moment, suspended in the deep, it looked delicate, fragile, almost beautiful. The scientist Aaron Evans, who helped verify the species, hyperventilated while watching the high-resolution footage for the first time. It took 100 years. But we finally saw it. Besides making creatures large, the deep ocean also does something else to them. It makes them alien. Consider the fangtooth fish, for instance. Barely 15 centimeters long, yet it possesses the largest teeth relative to body size of any fish on Earth. I mean, those fangs are so disproportionately huge that the fish cannot close its mouth, and special pouches have had to evolve in the roof of its skull to accommodate the lower teeth. Otherwise, they would pierce its own brain. The gulper eel takes this even further. Its jaw is 1/4 of its entire body length, connected by elastic ligaments that allow it to expand to 11 times its normal volume. When prey approaches, the jaw inflates like a balloon, engulfing creatures larger than the eel itself. Footage captured in 2018 shows it expanding and deflating like a living net, a pulsing black void in the darkness. Then there is the barrel-eye fish with its transparent skull. Inside a fluid-filled dome, its two barrel-shaped eyes point upward, watching for silhouettes of prey against the faint glow above. What appear to be eyes on its face are actually nostrils, and the transparent dome evolved to protect those delicate eyes from the stinging tentacles of siphonophores, colonial organisms that trail 10-meter-long threads through the water. Practically nothing about this creature makes sense until you understand it evolved to steal food from animals that can paralyze with a touch. However, the balance that created these monsters is breaking. The deep ocean is not unchanging anymore. If anything, it is changing now, faster than it has in millions of years, and the creatures built for stability are beginning to fail. Earth's oceans have lost 2% of their oxygen in just 50 years. The zone of suffocating water off West Africa has expanded by 1.7 million square miles. And even if we stopped all emissions today, committed warming means the deep ocean will lose more than 10% of its oxygen by 2065. And as we know, warmer water holds less oxygen, but warmer organisms need more oxygen. So the equation that built the giants is reversing in real time, and that will be a problem because large bodies require proportionally more oxygen than small ones. So in a world where oxygen is declining, size becomes a liability. The giants that survived for millions of years by growing enormous may no longer be able to sustain those bodies. Antarctic sea spiders, those dinner plate-sized creatures that breathe through pores in their skin, they are already showing signs of stress. Scientists study them as bioindicators, watching to see if they begin to shrink as their oxygen-rich world warms. On the other hand, the colossal squid combines polar gigantism and abyssal gigantism. It exists at the convergence of two extreme environments, both of which depend on cold, oxygen-rich water. As temperatures rise and oxygen falls, that convergence may cease to exist, and we are watching it happen already. The deep sea is the most stable environment on Earth, and its creatures are accustomed to a world that never changes. But stability is not resilience, and when change comes to a system built on constancy, collapse follows. The monsters of the deep are fragile giants, held together by conditions we are destroying, and once they disappear, they will not return. The colossal squid, the giant isopod, the creatures we have barely begun to discover, they may vanish before we ever truly know them. The ocean made monsters by necessity, but now necessity is changing. The darkness is vast, and it is emptying.